You bet. Oh, really? It's so good. You should. It's due on Saturday. Yeah, it's great. Yeah, lazy. Yeah, so did I. And I cranked that a lot in the last couple of weeks. It's funny. I was like, why is it? I was trying to think like how it was possibly display the sum even if you're doing other stuff after. I guess you can just move the value to another register and then move it back at the end.
Yeah, for the look, I called this function first it into like I said, and then I called this up. Within a second block.
That's what I was thinking. I would just move once I had the sum in zero, I would just move it to like you said, 15 or whatever, and then at the end move it back to zero, right?
Yeah.
Before you return. Then it would still do the sum.
Wait, hold on, I was just listening.
Okay, so if you still wanted to split the sum instead of the mean, since that's what the sample output has, before you start messing, like after you get the sum, you store it into like X amount of 15 or something, and then you do like the mean and whatnot.
Yeah.
And then after that,
You store my
you put 15 back into it. And then you return.
Yeah, and then it goes back in.
But yeah, but it'll be the sum.
Um.
It'll-
I think we do like I think that we.
Yeah, but whatever, before you do that, you just store the sum value somewhere else.
Yeah.
And then at the end, you move that value back.
Yeah.
You can.
I think.
Oh, okay.
Yeah, because you're saving and then calling it back.
Well, good morning, everyone. It's 10 o'clock. Let's get underway. I don't know if you pay attention to ECS week. This week, this school of ECS, the College of ECS, has a special week. Something happens every day, and I haven't looked at the schedule, I have to admit. But many times, one day is set aside to a career event. If that happens, I think that's the one I recommend you go to. In fact, you should make a habit of going to all the career fairs. Even if you're not graduating for another 2 years, go to all the career fairs and learn the environment of how to talk to those people, what they're looking for. You'll learn a lot just by a 3-minute conversation with somebody at a career, at a table advertising his or her company. Then when it comes for real, you'll be very acquainted with the protocols. Okay, so I'm gonna leave that. And then Wednesday, just a reminder, it's a class on Zoom only. There's 10 of you here in the room. You got to find some place to go to class. Room 202 in this building, one floor above us, should be available. I have no reason why to think it's not available. Or you can go find a cubicle in the library and put yourself in a corner with not much foot traffic and go to class there. And let's see. Oh, tests are coming in early March. Okay. So last of all, let me make my screen bigger. See, I admit that I didn't do a really top line job on input array. It was spread over 2.5 lectures. It was kind of disjointed. If I had it all worked out on one day, I would have taken the entire one lecture to do it all. But the the warning is that's the tough piece out of assignment 2. You should get started early on that input array. Right now, I've got other stuff to do. I'll tell you about it. I don't know what happens with Discord because I'm not ethically supposed to go there, but occasionally a student comes to me for advising on other matters, and I ask, how's Discord going? And they tell me some really good events. Some, I'd be glad for your 3 SI leaders. They were holding extra SI sessions. One or more of them were holding extra SI sessions late in the evening. And another student during advising time told me that he was getting tutoring help on a weekend late at night. So I think they're top of the line people for getting help. Don't overlook that as a resource. Yes, leaders. Many of them are there in Discord many hours a day on their own time. That's not their officially required duties. Okay. Having said that, we'll go on and okay, where I left off recently, well, we're back to the textbook. Where I left off in the textbook was around section 3.3. And it described a NAN. I don't know if I described a NAN, but in the next 60 seconds, we'll do it. There's a number line, zeros in the middle. There's a special number equally distant apart. This one is known as smallest positive normal number. We should compute that and express it in ordinary decimal. Out here is just the end. No name to it. And somewhere here is positive infinity. So normal numbers are caught between here and here. Normal. The negative sign is a mirror image. It has this, the negative of that number is here. The negative of infinity is here. And over here is the end. Okay. The area in the, at the end, towards the ends. I want a different color.
Did you read the paper down?
Oh, yes, thanks for reminding me. Between the end and infinity is the area of nans. And the mirror image happens over here. Those are NaNs. They're not numbers. You can't add 2 of them together. But occasionally you get the issue of 2 normals multiplied together equals a nan. And it's not an error. The machine, your program keeps running, and you can call printf, and you think you're going to print the product of two numbers, but all it outputs are the three letters NaN. So you can overflow it by some math operations. We just need to know that they exist, but there's not much you can do about them. They're bounded by plus infinity is part of NANS. Negative infinity is part of negative NANS. Okay, let's go on. Section, not dollar sign, section 4.4. I think I'm telling you things you already know. How do you declare pi or any other odd float number? Pi dq 3.1 6, whatever. Okay. So that's pi. Pi points to where 3.1416 is stored. So this is an address, that's what's stored there. And of course, you want to work with it in an XMM register. Get it again. SD, pick one, XM, 14, comma, I. Okay, then it's in an XMM register where you do work with it, you probably already know this. Section 4.6. The author talks about assembly without C and without C++, which is known as pure assembly. In other words, the driver is written in assembly. And if you do that, the author explains what to do here. If the driver is in ASM, then you make a couple small changes. You have to declare as global underscore start. And then you declare it in segment text. The name of your function is underscore start. And it's underscore start with a colon, of course. Okay, so what we're programming in this semester has been hybrid assembly. But in the world, not everybody does that. It's a good place to learn assembly, but some program in pure assembly, which means simply there are no functions written in C or C++. There's no library functions from C or C++. It's just 100% assembly. Okay. So he has a short section in section 4.6 about this and what you have to change over to make it work. It's namely the start declaration and the start declaration here. We'll come back to that later in the semester. That's the end of chapter 4. Chapter 5. The name of it is tool chain. Let's see if we can do this in 15 minutes, probably. Okay, the tool chain he describes what things you already know. He describes what is an assembler. Well, we're using one of them, NASM. The author claims, he says, I believe him, he's using YASM. And if you're working with Microsoft tools, you'd guess it's MASM. Okay, and that's right. There's various competing uh, assemblers on the marketplace. This one is free. I don't know the others, but anybody can download a NASM and use it. He talks about what is a linker. And I hope my demonstration works in a few minutes, and we'll see what it actually does. It has to connect missing pieces together. When you have a call to printf, there's it's marked with 8 zeros in the object file. It marks this place with 8 zeros, but the linker has to find the starting address of printf and place it in there. So it completes the job of assembling because it connects outside pieces together. Well, I hope that I'll show you how that works. Okay, we need a linker. We've been using the linker from C++ or from C, but if you're writing pure assembly, then you have to use the linker LD. That's, if you've installed NASM, LD was installed with it and you don't know it, but it's still there. This is a linker for if every O file came from assembly, then this would be the linker to use. Okay, there's not much we can do about loader. Okay, so here, back up. Here's the whole screen. The loader is part of the operating system of OS. And its job is to copy your source, not your source. It's to copy your executable file from hard storage to memory. Copies the executable. You went through this linking process. It creates an executable file. And then the loader has to copy that from hard storage to memory. And there's one other little trick. Now it's sitting in memory, so every byte has an address. It finds the address of the first instruction and copies that address into RIP. Not the instruction itself, but the address in memory. First instruction. Into, okay, we don't have much control over this, and the author only gives about a third of a page description about it. ELF 64. You've seen in the assemble directive -F ELF 64. This is a format for object files. And it's this particular one is quite common. Uh, other languages use the same format file. And when they all use the same format, it's the linker can link these together quite easily. So in case you're one, there is an ELF. I forgot what these letters mean, but it doesn't matter. There's another one for 32 if you were writing code to run on 32-bit machines only. But it's kind of obsolete. Okay, what else do we need here? There's a command -L. .lis. Okay. I hope to show a live example of one of these right today. It says create a list file. I don't know why that name is used, but it doesn't matter. And the list file has two halves. It will have a column over here, which is assembly instructions. Instructions in hex. And then over here is a larger column. It will have your coding for each instruction, line by line, horizontally across the page. So this is assembly source over here. So if you write something simple like move RBX R14, you can look across the page and find out how that was assembled. Now, this backwards engineering is not easy, but sometimes you can pick out the piece that means move, and the piece which means RBX, and the piece which means R14, and smash them all together, and you have one large structure usually in hex, which is this instruction over here, what it translates to. And the author makes this comment, which is very clear. Only in assembly do you find a one-to-one correspondence between machine instructions and programmers' statements. Correspondence between executable instructions and programmer written instructions. Okay. One instruction here assembles into one here. That's not true in higher languages. Between programmer statement and executable instruction. That's going across this way, both directions. And executable instructions. Okay. And then let's try it. Okay. The class that was here before you, I had lost the file, but I think I have it now. So we're going to hang with me here. Let me see if I can start this up. And I'll share the screen with you. Okay. So here is this first statement. Yeah, I have to unmute myself. Okay, I think you're seeing this simple beginner program. it had a previous purpose, but I inserted some things we could experiment with. All the general purpose registers and so on. So here where it says experimental, down to this other dotted line, that's stuff I just inserted for the fun of it to see what happens. We're going to look at the instruction that's in the list file for each of these. And I used R8 and R10 and R9 repeatedly trying to find the code number for that specific register. But it's not totally successful. Let's see what it does with like a large integer. That does that overflow 32 bits? I think it does. I think this one does. I think this one does. Let's where's my unity? Oh, that's the wrong place to look at it. Let's go back here. Okay, open the terminal. Stretch that thing if I can. Stop shaking. Okay. And the R file has message. It has -L hello list. Okay, that's one we want to look at. So let's no, I want to /R.sh. And what's the issue here? Okay, it doesn't have permission to execute. Let's verify that is okay. /R.sh. We don't care about this. Okay, what we care about is the list file. It's here. And stretch this some more. Okay, I hope I think it's going to be okay. Okay, it's right now we're just looking at line numbers because this is all comment stuff. And actually, this is non-executable material over here. It has no translation yet. We don't think so. Is this? Yeah. Okay. Anyways, the segment data, it translates each string into ASCII. And so this is an offset number from the beginning of source code, beginning of executable, counting bytes. Line numbers are not that important. And then this is the code for that code over here. Okay. It's in big Indian. You can read it straightforward. That uppercase T is 54. And the next letter is H, lowercase h is 68 in hex system. So you can follow byte by byte on the left column what's happening on the right. Okay. And then over here, you notice there's a 10. How much is 10 in hex? 8. A. Here it is. There's the 10, and then there's a 0 byte at the very end of the string. Okay. It's all there. Okay, so we keep on going. Okay. Oh, and this segment renumbers itself. So here we renumber our starting position. That's minor stuff. Okay, I don't fully understand the angle brackets for this, but here's reserving 832 decimal bytes is 340 hex bytes. And by the way, lowercase h at the end of a number is equivalent to a 0x at the beginning of the number. It just says that 340 is written in hex. Okay, that's okay. So we should restart the offset counter at 0 again. And 55 is the instruction for push RBP. And that's kind of strange. I was hoping to have 2 bytes. There's a 1 byte instruction. See, nearby is push RBX. I was looking for an instruction for push and another one for the operand RBX, but they're not. The 2 together makes 1 instruction code. Okay. Back here, there's a move on. Now I'm making what I think is an intelligent guess. I think 48 is move, 89 is RBP, and E5 is RSP. And the assembler looks up that stuff and puts in the hex file what it assembles to. So this is assembly, and this is assembled. That's binary code. Here's some, somewhere in the year 2005, there was a big changeover. And a lot of instructions before that time were 1 byte, 2 hex digits is 1 byte. But then in that year came the new registers R8, 9, 10, 11. So now they have 2 byte execution codes. But pushing the flags register was an old one, so it still has 1 byte as its execution code. Now, if you took all those and lined them up across the page, a 55 and this number, no spacing between each other, and line this number right after it and this number right after it, you'd have the executable file, with the exception of function calls. What is this? Put a 7 in RAX. B8. I bet that without a doubt that's move RAX. But the real parameter is here. And this is old code before 2005. That's 07. If you look at it, the highlighted part is 07 in little Indian, 32 bits. So we'd have to turn them around in pairs and read it 00, 00, 00, 00, 07. There's our number. And because it's less than 2 to the 32, they're only going to show us 32 bits. I have a big number coming just for that purpose. This is putting a 0 in RDX. BA is moved to RDX, and then there's the 0 parameter. Okay, and say Xsave translates to this mess. Now, you think that's junk. It's actually, we're going to prove it now. I think that's the offset we're to find backup storage area. If you take 000, see next to the backup storage area, that's the offset in bytes from the start of that segment. Okay. If we were moving something into this other thing called username array, that number in square brackets would be 340. But here's how you interpret that. This is an address within this same file. It's not calling printf or something like that. Okay, so here starts my experiments. Here is putting 9 in R8. Take it, 9 starts here. That's 41B8. The next one right below it is R9. It's 41B9. I think they should be related. 41B9. And the next one is 41BA. Oh, but that's registered. Oh, yeah, that's one later. Okay, it's counting 8, 9, 10. 8, 9A. There's the 10. And then an add instruction is, I only have one example, so I can't compare it to try to decipher what it means. But that's an intelligent guess is in the table, the assembler has found ADD and placed it, looked across the table and found 4D. Now, how does it get 0, 1 and CA out of R10 and R9? I don't know. Okay. We'll try one more. This much is, yeah. See, IMOL over here, IMOL occurs 3 times. And the part that's constant here is 4D0F, 4D0F, 4D0F. So that's probably reasonable shot is that that's IMOL. And then what is, I don't get it here. AF, AF, AF. That there's 3 AFs. I can't figure it out. You don't always get them right. I can figure out maybe half of these, but not all. Not all. Some I never figured out. Okay, so here is when the hard-coded number integer is greater than 2 to the 32, it means you need more than 32 bits. And therefore, you see here, number 9 back here is encoded in 32 bits, little endian. Now, here comes a large number, and suddenly we have 64. How many bits we have? We have 64 bits for this integer number. And where does it start? I can't be sure. That's 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, 6, 7, and 8. By the way, the trailing hyphen is a continuation mark. These 2 zeros belong at the end of this number back here. Yeah, there's 8 bytes for 0. Now we have to go through some kind of translation to translate decimal 8 billion here to hex. And there's a good chance it's going to be this one. I can run a program later. We'll translate 8 billion, and then there you have 8 billion. So the first part was the move and the R9, and then the 8 billion. And I'll leave it go there. Okay. Let's try a 12-digit number. Same story. This 49 is R15, and excuse me, that's move. And then the R15 is BF. Okay. It's BF. And then there's a 64-bit number after it, which is this mess over here. You know what, and even at that, you have to read that number backwards. If we put it in a calculator, the decimal one, and ask for it in hex, it's going to be this one over here. The leading byte is 00. The next byte is 00. Next byte is 00. And then the next byte is here. It's still going to be backwards. Okay. Well, you know what my -1 is, don't you? -1, like +1, is less than 32 bits. So they only show you half of the digits. I'm not quite sure why, but there's some economy going on here. Whereas this requires more than 32 bits. And hence you get this long expression that continues on the next line. Okay, -1 is 1111111. But they only show us I'm sure it's intentional, but it's very confusing. They show us this short -1. And here's a short -1. And the register went up by one number from C2 to C3. That kind of makes sense that R10 is C2 and R11 is C3. Well, I need to tell you what the double arrow means. That'll make more sense to you. Yeah, I'm going to stop it just for one instant. And what do we have? 3 arrow. I don't know why they don't use 2 to the. I don't know why assembly doesn't use this. But it doesn't. Okay, so if we wanted 2 to the 14, it would be 114. Is that under the? Okay, it's a nice way to get powers of 2 entered into the discussion. So I'll go back and share this again. Share. Okay, I think we're back. Hello, can you hear me, Professor? There is no voice. Every time it's a machine problem, me locally. Thanks. Oh, I'm sorry, you guys online. I wasn't looking at that part. Okay, we were working through several of these cases. If you're online, several of these cases of how files, how functions to be called are not known at assemble time. And some clear examples would be printf here. This goes into the object file and into that standard format ELF64. Anyways, the linker is going to fill in all those places. And if we had, I don't know if we have the time, let me take. See if I can record the location of one of these. What is an instruction that's okay? Right under my jump is move RDI to welcome. So that's 48BF. 48BF is some kind of welcome message. Okay, you're still with me here. Okay. Okay, for those of you who are online, that's what was happening as I was looking at different instances of calling functions and observing what happens when the assembler doesn't have that function with it. Okay, let's now take this one. This one doesn't open as nicely. Okay, we'll open it here. This is the executable file. All this stuff has been linked in. And I was interested in the welcome message at 48BF. Let's see. That's the very first one where the blue highlight is. This isn't my, is this GHEX? Fine. 48B. A lot of 48BFs. I won't know which one it was that one. That was supposed to be the welcome message. Okay. This message 48 40 40 0 0 0. That can't be it. 486 40 48. No. I didn't know those that many. This okay. Where's my where's the old one? That was supposed to be the welcome message. Here it is, 48BF, and followed by what welcome is. But I don't know which one of those many 48 B, there's 49 BF. It was. No, let's, one more try. Okay, maybe this is more rare. Let's go BE30. That's the instruction to move RSI to RSI. BE30. What did I say? BE30. 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 There it is. And it references 00048. I think that's the string that follows it. Over here is on the side is move. Oh, it's BE30. Name of string size. Let me get one last name string size. What was that? Oh, that was the number 48. BE30 should have been followed by a 48. Okay, so back here, what did it? Well, it's pretty close. It's a 48. And I don't think those BE830. Yeah, it's 32 bits, but it's strange. 0000. 48 was already hex, and there it is. I take more study to find what the rest of this, and then the next instruction will start. If that's 1, 2, 3, 4, 1, 2, 3, 4. Next instruction was C. That's a deep reference. Well, class, we're running out of time. Oh. I didn't prepare well my punchline. Punchline. I was going to change the code back here and then run it. And instead of saying welcome to programming, it's going to say goodbye. If you're very patient and can track things, you can modify the executable, which is what we're looking at right now, is the executable, and make it do other things. And I once worked for a company, Pacific Care Insurance, and they had lost the source code for one of their major accounting programs. And those poor programmers were told to go fix it by fixing the executable file, which they still had. So those poor guys, well, there's probably some women there too, had to study that to the point where they could understand what messages were and where the modification was happening. And then they were told to upgrade it in place. Then I left that company and I never heard what happened. But the last I was there, they're still maintaining the program by looking at the executable file. It's this stuff here. Okay. So I felt sorry for them, but that's the worst. That's tough programming if you can do that. Okay. You know what the list file is now? That was supposed to be the big story. The list file is right here. It has two major columns. The right side are your assembly instructions, and the left side is what the assembler is doing with it. It's creating this middle column. The middle column is here. The leftmost column is offset. That's just counting instructions in bytes. The assembler makes all of this. Okay. It's pretty good stuff, except things are incomplete. It doesn't know what to do with FGITs. And it doesn't know what to do with string length. That would be here. So it's a postponed job for the linker to put that together. And if you are patient, if anybody is patient enough, you can find out where string length is. You have to go find this instruction. What was the one before it? 48BF. And soon after that, you'll find what was put in there as the starting address of string length. Okay. We're gonna stop here. Anybody have a question? Take the course in malware analysis and you match malware patterns to source code to see if it's infected, not the source code, to the executable code to see if it's infected, is you're looking for a match to a known virus string. And that's a fun program to make. I think it is fun. Okay. Let's stop here. Okay. You give me the, I'll give you the question, you give me the answer. Where's my list? Put your answer in chat messages. Where's my chat anyway? Oh, there it is. Okay. The first question is, who created the first program? Who created the first computer? Nobody has an answer? Put the person's name in chat messages. Oh no. This midterm's not going to go very well. Joanna says von Neumann. Almost, but no. Anybody else don't know who this is? Wow. He's not American. Does that help? Alan Turing. No. But I have a reasonably good guess. Joanna has hit it on the nose. Chucky. From Chuck E. Cheese. Okay, so Chuck E. Cheese Batman. That's right. Okay. So who created HTML? You chose this major because you love computers, and you have to know who made all of this possible for us to have so much fun programming computers and have a wonderful job in the future that pays for everything because of computers. Who got us there? Who made HTML? A rephrase of that is, who made the first web page? That might not be a good rephrase. but it's pretty close. Nobody's, yeah, that's right, Joanne. And Zachary too. Tim Berners. He has an attached name. I don't know. That's his wife's name, I think. Doesn't matter. Oh, okay, that's great. Who's the first programmer ever? Dr. Bain of the computer science department. You got that wrong. Who's the first programmer? Man. Now I know why so many people take this course twice. They don't really like me. I thought they came back to see me, but they don't know themselves. Yes, Joanna, it is Miss Ada. Actually, Joanna has a speed index into Wikipedia. Okay, that sounds pretty good. Who is what one person is the most responsible for open source software? Who lots of people work in open source software, including all of you, because you're using open source NASM. But who's most responsible for putting all this stuff in our hands? Who should I write? Not Chuck not Charles Babbage. No. Sullivan, that's great. Oh. You know, he was the director of the MIT AI lab. The whole story was that he wanted to fix the printer. The manufacturer of the printer says, no way, we're not going to give you the spec sheet. You call our expensive repair person to come and fix it. And Richard came unglued and said, that's it. The world needs software. We had to write software for the printer. The world needs software that's open to everyone and free of charge. And he spent a career making the open source side of the world. Tim Berners is still active. Active. You know where that was? Where was the first website? It was at CERN in Switzerland. All right. Who created? It was my list. Not that one. Who created C++? C++. Your favorite programming language is not Richard Stallman, but it is Muhammad. That's great. Barnes Strustrup. It's the name I can never spell. I'm sure I spelled it wrong, but that's pretty close to it. Okay, great. Who is the father of algorithms? One of your favorite classes you'll ever take is 335, all about algorithms. His name sounds like Al Goro. Alkozami. Oh, that's too far back, man.
Algo.
Al Go. It's like algo. Funny guys here. Okay, now I'm aware of Al-Khwarizmi, but he's too far back. He wrote algorithms before there were computers. Okay, this is in the computer age. Yeah, that's it. Haley, Donald Canoe. Wrote a huge volume of all these algorithms in the world at the time he was working on this and laid the foundation for future research into more advanced algorithms. Um, yeah, okay. Yeah, he was a professor at Stanford. My office partner many years ago went all the way to Stanford to stand in front of his door with the nameplate there and take a picture of him. So he never got to see Canoes. Canoe's too busy. Okay, so let's try something more reasonable. Are you? Oh no, this is a hard stuff. Who is known as the theoretical founder of AI? The lay the theory foundations for all future AI. Now you know this guy's name. You probably just never connected it. That's right, Salty Man, and Joanna too, both of you. It is Turing. That's right. Okay. Now he didn't build smart chat GPTs or anything, but he laid the theoretical foundations of how this could be built in the future, and that's pretty good stuff. Um, now we go for the real killer. How dead would our life be if we could not communicate electronically? I've actually lived in that time period. Who created TCP/IP, which is the communication protocol for electronic data transmission? Who, I'll rephrase it, who invented the internet? These two protocols for handling transmissions had to be invented. How dead our lives would be if we could not send messages electronically. Yeah, Joanna, that's actually 50% right. Okay. This is a trick question. It was a team of two. Person X was kind of like the bossy person, and Bob Kahn did all the work. Yeah, Benton Cerf. Okay, how do you spell that? Khan. Okay. So Benton gets all the credit, but the record shows that Bob Kahn did all the work, did all the hard work. Okay. There was a picture in a magazine 6 months ago. Those two guys showed up at the same computer conference, Berners-Lee and Benton Cerf. Berners-Lee was wearing a t-shirt that says, I invented the web. Benton was wearing a t-shirt that says, I invented the internet. Take it for what it's worth. And they had a picture taken. There's two standing side by side. All right, well, we get to who was the first assembly programmer? Assembly programmer, the first one who wrote an instruction, the very first instruction that had to required an assembler to get the binary code out of it. And, yes, you guys got it. That was Kathleen Booth. When she was around 20 years old, living in London, she got a job in a tech company and they said, we need a programmer. And whether she was forced into it or she volunteered for it, I don't know. I don't know that history. But she started programming in assembly, the first one who ever did that. And you know what? She kept working in assembly for quite a few years after that. She got married, middle age, kept working assembly, moved to Canada, got another job. It still said, we need somebody to work in assembly. She worked in assembly until she was 100 years old. And as error message came up, seg fault, and she put the pencil down and says, I quit. A few days later, she died. I think the year was 2022. Yeah. That's a long time programming and assembly. Okay, so my favorite. Who made life easy so that we could plug in all kinds of stuff into a USB port, like a coffee warmer or a dancing Santa Claus you can get at different stores, and it's a USB plug. Who made USB? We owe this guy a ton of credit. We wouldn't have flash drives with USB connections or anything else that connects with USB if he hadn't done it right. That's right. In fact, old AJ. Yeah. Is there two T's on the end? I must have. I never was good at spelling. One T, but what do I know? Yeah, he employed at he was employee at Intel. Went home one evening thinking about this problem that's 15 different cables with 15 different interfaces to plug into the rear end of his computer. He says there's got to be a better way. He invented, just set out and says, I'll invent a plug that does all the communication. And it worked. That's a good guy. Okay, so we're getting, where are we now? Okay. I'll get to the end of this. No, I'll leave out. Grace Hopper was a great lady, admiral in the Navy, and a big programmer on those early computers. We'll go on. But okay, there's a company called AMD. And you may have its microprocessor in your computer now. In fact, as of this year, only two companies make these. That's the x86 processor. Okay. You know the story of Intel, but we'll do that another day. Around the year 2017, AMD was in great financial problems. When a company has more debt than the total value of all of its property, it's really in bad shape. The bank is soon going to come and take the property to pay the loan. Got it? AMD had reached the bottom at that time. Then they hired this person who you know very well to come and take over the company as CEO and take the whole thing. It's going to fall apart. It's going to collapse. The bankers are going to take it and turn the buildings into coffee shops. So this person came and went. This person is highly educated. Went to the lab. This is not a Steve Jobs who doesn't know a thing about technology, but he knows a lot of business. This person knows a lot of business and went into the lab and said, look, guys, I'm going to design the next x86 microprocessor from this company, the Ryzen 2000, or whatever the number was. That processor sold big time. The company started to pay off its debts as this individual continued to design the microprocessor successors up to the present time. And the company is now got lots of cash and owes no money. We can say the company was saved. Who is a hero? Yes, Mohammed, you already know the story. Lisa Su did it. Lisa Su is a computer scientist. She went in the labs and told those engineers, here's how it's going to be. Build this one. And that one was so good it sold, and the ones that came later were on her design. If you visit Boston, you can find streets named Lisa Su. If you go to MIT, there's a huge building called Lisa Su. This person understands assembly and architecture very well. She belongs on the heroes list. And I've got half a dozen more, but I think we'll just pause here and save them for another day. Stallman, MIT is great. It's a great school of technology. Stallman came from here. And now her name is on the building, on the AI building. It's not the whole university, but it's on this one specific building. All right, everyone. Have a great day. We're finished with the lecture. Know about the heroes. Why should you know that? Well, the short answer is it's on the test. And the long answer is we owe a debt of gratitude to the people who made it possible for us to be here and pursue a wonderful career. Have a great day, everyone. See you on Wednesday virtually. No in-person class. Just